Minasan, konnichiwa, Zamurai Engineer desu. In this video, let us resume the discussion on module number 4 about failure of structures. So we already taken a look of this slide. So let us go faster to the point wherein we stop. So let us continue here. These properties, this analysis would tell us about the possibility of several occurrences of different failures. Okay? So it would depend on the analysis. Okay? So usually we have design concept and rationale. So we have several analysis. So we have 5 analysis methods. 1, first order elastic analysis. Number 2, first order plastic analysis. Number 3, second order elastic analysis. Okay. Number 4, elastic stability analysis. Okay. And number 5, advanced analysis. Looking at the member behavior, we can have what? Some sort of congruence. Okay. So the first order elastic analysis could be used in order to analyze number 1, so linear properties. Okay. So there's a linear portion of the property of material. We are looking at again the stress strain diagram. And number 2, we have what? Material non-linearity. So this portion going here. Okay, so that is congruent to the what? First order plastic analysis. Okay. And number 3, geometric non-linearity. So we could use what? Second order elastic analysis for that. Okay. So picking out the correct analysis method that would correspond, okay, to the member behavior is what we need to appreciate. Okay. So we should model an analysis method that would directly correspond to the behavior of the member. For example, if the member is number 3, geometric nonlinearity, and you use first order elastic analysis or first order plastic analysis, it would only be able to predict the behavior of material up to a certain point. For example, up to this point. Okay, up to this point. So up to this point. So afterwards, the behavior of material will differ greatly on the model. So for example, the material is a buckling. So we have to predict it by using what? Elastic stability analysis. So it is therefore very important for us engineering designer to be able to pick the correct appropriate model, the method that we're going to use in order to predict the behavior of material properly. Okay, so making the mistake, choosing the incorrect model or analysis would be tantamount to failure. Okay, so material behavior, for example, is number 5. Okay, material and geometric nonlinearity, and you use second order elastic analysis. So it is accurate up to this point, then afterwards it will what? Will not able to predict it accurately, and therefore if you use that the structure may be susceptible to failure after this deformation, after this amount of deformation. So this point of deformation. After additional deformation, after this point, so our prediction will be what incorrect, and therefore may what may result to failure of the structure. Because incorrect computation, incorrect analysis. So, for example, we have what? Number 6, polyplastic behavior. So, polyplastic behavior is almost similar to behavior of buckling, but about what? What about 75% only of the buckling? So, 25 to 30%. But discrepancy is too much, so could not properly predict the outcome. Okay, so it would result in failure. For example, number 7, local buckling. If you predict elastic stability analysis and then the material as local buckling, so it's totally a mistake. Okay, so how to predict local buckling? We do not have the analysis method for local buckling. So therefore, we might modify the advanced analysis to be able to come up with a similar prediction for this type of member behavior. Brittle fracture, we can use a linear, we can use any type, but stop at some point. Stop at the breaking point. Stop at the rupture point. So all of the analysis method could predict brittle fracture, but stop at a specific deformation. Okay. So those are the concept, and with respect to strength, stability, and stiffness, we want to ensure that our structure would be able to withstand these three design perspective. Okay, so design for strength, design for stability, and design for stiffness. So stiff, strength, stability, light, all okay in this example. So can we compare? Not stiff enough, need bigger E. So the material property, which is what we call elastic, modulus of elasticity. This is the modulus of elasticity. So the greater the modulus of elasticity, the stiffer the material. So if the material has low modulus of elasticity, meaning low stiffness, so this is what happened to the wing of the supposed to be normal airplane in operation. This is the normal airplane in operation. This is now an airplane with low stiffness on the material, on the wings. Okay. What about not stability? So unstable. Okay. So if we are unstable, so meaning left and right side but loses its balance during the operation. So when that happens, that is not stable. So it is supposed to retain its balance throughout the operation. Okay. And next, not strong enough. So meaning slow value of yield stress, your yield strength. Okay. So we need higher yield strength. Okay, yield point. So if that is not strong enough, the wings would, for example, break. So that means we need a better material, a stronger material. So, okay. And lastly, too heavy. Too heavy, it will not get off the ground. It will not get off the ground because it is too heavy. We need what? Lower raw or density. We need lower density. So we should be able to choose, design a material with lower density so that the engine could be able to carry the self-weight. Okay, self-weight is just a load and in addition to the passenger, pilot, crew, and the luggages. So this airplane should be able to carry those total loads. Okay? So if not, we need to choose another material that would be what? Light enough in order to minimize load. Okay, so these are the concept when we are doing the analysis of the design. Okay, so that's all for what, because mistake on those different factors would give us the what? The failure. Buckling is a failure mode. What else are the failure mode? Strength, failure, that's failure mode. Plastic, so rupture, is failure mode. So core strength, that is rupture, that is on the what? On the plastic region. Also, if the material is brittle, so failure mode. So we will discuss what is on the viral video with similar relationship related to what we are discussing, the properties that we are discussing right now. Anyway, we have the current slide. Please answer the following and put your answer on the comment section below. So what we have here is question number 36. What is the recommended length of road section where reflectorized rumble strip? This is a typo error. This is rumble strip. So what you are seeing on your monitor, on your screen is what? White lines, which are actually what we call rumble strip. These are not just paint. Okay, these are rumble strips. Okay, so what is the recommended length of road section where rumble strips are to be installed? A, 10 to 20 meters, B, 20 to 30 meters, C, 15 to 20 meter, 25 meters, D, 15 to 30 meters. Okay, that's all. Again, this is Dr. AP, preaching engineering for nation building.